Hello everyone. I am going to discuss operation of single phase full converter under discontinuous and continuous current modes. Before going to full converter, I want to look into few basic concepts. Thyristor is a three-terminal device. Its terminals are anode, cathode, and gate. And whenever anode is positive with respect to cathode, thyristor is in forward blocking mode and acts as a open switch, and the voltage across load is 0. Whenever turn on is required, a small pulse is applied to its gate, and thyristor is switched into conduction and acts as a switch. The load is subjected to source voltage. Compared to diode, thyristor has a controlled turn on. Once thyristor is turned on and the required power is transferred to the load, the thyristor can be turned off. There are two ways to turn off thyristor. The first one is when thyristor current becomes 0, thyristor is turned off. And the second one is when thyristor is reverse biased, when anode is negative with respect to cathode, similar to a diode. This is a circuit diagram of single phase full converter. It has 4 thyristors, T1, T2, T3 and T4. The input voltage is varying sinusoidally with a peak value of Vm. During positive half cycle, terminal P is positive with respect to Q. So thyristors T1 and T2 are in forward blocking mode. In the negative half cycle, Q is positive with respect to P, and thyristors T3 and T4 are in forward blocking mode. So in the positive half cycle, at omega t equals to alpha, T1, T2 are on, and in the negative half cycle, at pi plus alpha, T3 and T4 are on. In the positive half cycle, when T1 and T2 are turned on, the load is subjected to source voltage through T1 and T2. In the negative half cycle, when T3 and T4 are turned on, the load is subjected to positive voltage. In the positive half cycle, when T1 and T2 are turned on at omega t equals to alpha, the load voltage suddenly rises from 0 to certain value depending on value of alpha. And as the load is resistive, the load current also suddenly rises from 0 to a particular value depending on value of resistance R. At omega t equals to pi, the load voltage reaches peak value, and the load current, which is in phase with load voltage, also reaches to peak value at pi by 2. At omega t equals to pi, the load voltage becomes 0 and the load current becomes 0, and T1, T2 are turned off. Similarly, in the negative half cycle, T3 and T4 are turned on at pi plus alpha, and T3 and T4 are turned off at 2 pi. Coming to the average output voltage, during period 0 to 2 pi, there are 2 identical voltage pulses. So to find out area under 2 voltage pulses, we can find the area of one pulse, and we can multiply with 2, and during alpha to pi, T1, T2 are on. So the limits for the integral are alpha to pi, and the voltage across load is varying as Vm sin omega t. So the area under tuples can be given by this expression, and the final expression is 2 Vm times 1 plus cos alpha. The average output voltage equals to area under 2 pulses over time period, and the final expression is Vm over pi 1 plus cos alpha. If firing angle alpha equals to 0, VDC equals to 2 Vm over pi, and if alpha equals to pi, VDC equals to 0. By varying alpha from 0 to pi, the output DC voltage can be varied from 2 Vm over pi to 0. Now let us consider single phase full converter with RL load. The voltage across R is defined as VR, and the voltage across inductor is defined as VL. The voltage across R and L is defined as V0. When the load is RL, the load current can be given by this expression. The load current has two components. One is sinusoidal component, and the second one is transient component, exponentially decaying component, and sinusoidal steady state component. Here alpha is firing angle, and theta is load angle given by tan inverse omega L by R, and Z is impedance. When the load is RL, there are two possibilities for load current. Depending on values of alpha, R and L, the load current can be continuous or discontinuous. If the instantaneous load current I0 falls to 0 between two voltage pulses of output, the load current is said to be discontinuous. If the instantaneous load current does not fall to 0 between two voltage pulses of output, the load current said to be continuous. These are the waveforms for discontinuous current case. This is the output voltage, and this is output current. If you look at the waveforms, at omega t equals to alpha, T1, T2 are turned on. When T1, T2 are turned on, the voltage suddenly rises to a particular value, whereas the current rises gradually due to inductance in the load, which will not allow sudden change in the current. At omega t equals to pi by 2, the load voltage reaches maximum, and at omega t equals to pi by 2 plus theta, the load current reaches maximum. The load current lags load voltage by an angle theta. At omega t equals to pi, the load voltage becomes 0. However, the load current is not 0 because of the energy stored in the inductance. So, as the load current is not 0, thyristors T1 and T2 continue to conduct till all the inductive energy becomes 0. At omega t equals to pi plus gamma, the inductive energy becomes 0, and the current becomes 0, and T1, T2 are turned off. During pi to pi plus gamma, the input voltage becomes negative, so the load voltage is negative. At omega t equals to pi plus alpha, T3 and T4 are turned on, again the load current rises. I want to divide the first current pulse into 3 intervals. Interval 1 between alpha to pi by 2 plus theta, interval 2 pi by 2 plus theta to pi, and interval 3 pi to pi plus gamma. Let us consider the interval 1 first during alpha to pi by 2 plus theta. And during this interval, the load current is positive and it is rising. As the load current is positive, the voltage across resistor is positive. The voltage and current in a resistor are always in phase. So the power of resistor is positive. It means the resistor absorbs power. And coming to inductor, as the current is rising, the voltage across inductor given by L times di by dt is positive, and the power of inductor is positive. So the inductor acts as load, storing the energy. This is the equivalent circuit during this interval. Here the current leaves from a positive terminal of the source. The current enters at positive terminal of the resistor, and the current enters at positive terminal of inductor. So during this period, the source supplies power to the resistor and inductor. Let us consider the second interval from pi by 2 plus theta to pi. In this case, the load current is positive and it is falling. As the load current is positive, the voltage of resistor is positive, the power of resistor is positive, and coming to inductor, as I0 is falling, the voltage across inductor is negative, the power of inductor is negative, that means it supplies power, and this is the equivalent circuit. In the source, the current leaves from a positive terminal, and the current enters at positive terminal of the resistor, and in the inductor, the current leaves from positive terminal. So during this period from pi by 2 plus theta to pi, the inductor and source supply power to resistor. Let us consider the final interval. The load current is positive and falling. As the load current is positive, the voltage across resistor is positive and the power of resistor is positive. And coming to inductor, the voltage across inductor is negative and inductor supplies power. And if you look at the equivalent circuit, the input voltage is reversed. So this terminal is positive and this terminal is negative. In the source, the current is entering at positive terminal, and in the resistor, the current is entering at positive terminal, and whereas in the inductor, the current is leaving at positive terminal. That means the source and resistor receive power, and the inductor supplies power. So at omega t equals to pi plus gamma, all the inductive energy is dissipated and the current becomes 0. the load current becomes discontinuous due to one or more of following reasons. The first one is the load inductance may be less. The second one, the load resistance may be large. And the third one, firing angle might be more. In most of the cases, discontinuous load current is not desirable. Coming to average output voltage, T1, T2 conduct during period alpha to pi plus gamma. So the limits for the integral are alpha to pi plus gamma, and voltage pulse is varying as Vm sin omega t. So if you simplify this expression, you will get this expression 2 Vm cos alpha minus cos gamma, and the average output voltage can be obtained by dividing with the time period, and this is the final expression for DC output voltage under discontinuous current mode. If the load current does not fall to zero between two voltage pulses, the load current is said to be continuous. The load current reaches a steady state value with a ripple. The steady state current or average current can be given as VDC over R. The average current depends on the average output voltage and resistance, whereas the ripple in the load current depends on the load resistance, load inductance, and firing angle. In continuous current case, the current oscillates around an average value. These are the waveforms for continuous current case in steady state. This is output voltage and this is output current. At omega t equals to alpha, T1, T2 are on, the voltage suddenly rises, and the current rises gradually, and at omega t equals to pi plus alpha, T3 and T4 are on. When T3 and T4 are on, T1 and T2 are off due to negative voltage across anode and cathode, and again at 2 pi plus alpha, T1, T2 are on, and T3, T4 are off due to negative voltage across anode and cathode. If you look at the current waveform, the current oscillates around an average value. The minimum value of the current is 28.5 for the particular values of the resistance and inductance. The maximum value of current is around 29. It is over little bit over 29. So the average current is around 28.75 amps. So in continuous current case, the current oscillates around an average value. The thyristors T1 and T2 conduct during period alpha to pi plus alpha. So the average output voltage can be given as 2 by 2 pi integral alpha to pi plus alpha Vm sin omega t d of omega t. If you simplify this expression, the final expression can be obtained as 2 Vm over pi cos alpha. If alpha equals to 0, VDC equals to 2 Vm over pi, and if alpha equals to 90, VDC equals to 0. If alpha is varied between 0 to pi by 2, the output voltage VDC is positive, and output current is positive, and power flows from AC to DC, and the converter is said to be in rectification mode. If firing angle is 180 degrees, the output voltage is minus 2 Vm over pi, and if firing angle equals to 90 degrees, the output voltage is 0. If firing angle is varied between pi by 2 to pi, the output voltage VDC is negative and the output current is positive. The power flows from DC to AC, and the converter is said to be in inversion mode. Before closing, I want to discuss one application of single phase full converter. This is a single phase DC drive. The armature and field are excited by two converters, separately converters. This is armature converter and this is field converter, and the armature voltage can be given as 2 Vm over pi cos alpha A, and by varying alpha A between 0 to pi by 2, the DC output voltage can be varied from 2 Vm by pi to 0 in forward motoring mode. In the regenerative braking mode, the armature runs due to kinetic energy in the load, and the field converter is still excited. So, as the armature is running and there is flux in the field, the machine acts as a generator, and the direction of field current is same, and the armature is running in the same direction. So the polarity of induced EMF in generating mode is the same as motoring mode, that is terminal A is positive with respect to AA. So the machine current in generating mode comes out of terminal A. Since there is a full converter which will not, as there is a full converter which will not allow current in the reverse direction. So the induced EMF polarity can be reversed by reversing the field current. When the field current direction is reversed, the induced EMF polarity is reversed, and by operating converter in the inversion mode, the power generated in the armature can be sent back to the source. Initially, the firing angle is kept nearer to pi. As the speed falls, the firing angle is decreased towards pi by 2. Thank you for watching video. Wish you good learning.